Dear students, so welcome to this lecture of digital communication. So we will start a new topic today, which is called OFDM or orthogonal frequency division multiplexing. So let's see what is OFDM. Okay, so basically it's a multi-carrier system. Okay, so that's the first term that you have heard new today. So what happens is that you have the total channel, okay, that you have, the radio channel, is divided into multiple, frequencies, okay, and the data signal is actually sent over multiple frequency. So the data signal is divided into multiple copies, okay, and each copy is each copy is modulated with a different carrier. Okay, so carrier means a carrier frequency. So that is what is all about multi-carrier system. So typically you have come across this concept of flat and frequency selective fading for a radio channel. Okay, so in your wireless communication module you have come across this. So for high bandwidth applications, the channel is frequency selective and the delay spread actually dictates the throughput. Okay, so if your signal bandwidth is higher, okay, let's say your signal bandwidth is higher than the channel coherence bandwidth, okay, then there is a possibility of this frequency selective fading. Okay, so to mitigate that effect, this multi-carrier modulation is used. So this is a technique where multiple low data rate carriers are combined by a transmitter to form a composite high data rate transmission. Okay, so that's the time domain part. So you have the signal which is divided into multiple low data rate carriers and are combined together to be sent through the channel. And in terms of the frequency response, so the available spectrum, okay, of the channel is split into several non-overlapping frequency sub-channels. Okay, and the individual data elements, so here in time domain you are dividing into multiple low data rate carriers, and here in case of frequency domain, the individual data elements are modulated into these sub channels, okay, and are thus frequency multiplexed. Okay, so OFDM, as we are studying in this lecture, this is basically multi-carrier modulation technique, and this created great expansion in wireless networks, okay, because it provides greater efficiency in terms of how many bits per second you can send over 1 hertz of bandwidth. Okay, and while we were upgrading from 3G to 4G, this OFDM is the main air interface, or it's the main physical layer transmission technology from 4G and onwards. Okay, so it is also a critical technology for broadband wireless access like WiMAX. Okay, so this is what actually happens. Okay, so as I was saying in the previous two slides, so you have a signal or a data that is varying at r bits per second. Okay, so this is the throughput, and you are using a serial to parallel converter, and you are basically splitting this data into several small tributaries, each of them having throughput of r over n bits per second. So you are actually dividing this r into 1, 2, 3 up to n tributaries, and each of the n tributaries has a smaller data rates, as you can see, because it's getting divided by n, and each of them has r over n. So if you sum all this r over n, okay, over I equal to 1 to n, then this will be n times r over n, so this will be r. So this is basically the sum of all these makes r bits per second, and each of this tributary or each of these copies are modulated by a different carrier frequency, as you can see. So the carrier frequency is centered along a certain central frequency, which is f0 here, and all of them are either f0 plus something or f0 minus something. So basically you have total n different carrier frequencies starting from f0 plus n minus 1 fb by 2 to f0 minus n minus 1 fb by 2. So basically your total number of frequencies here is n, okay, and each of these tributaries are modulated by these central frequencies, okay, and then all of them are added together, okay, all of them are combined together, and you are sending it through this antenna, okay. So so this is the concept of OFDM. There are several other things, other details here, but this is the high level concept of your OFDM system, okay. So as I said, so it converts a high data rate bit stream into multiple lower data rate substreams, as you just saw, and each substream is modulated onto a different carrier, which you saw in the last slide as well. So there is nothing new here. So now the concept becomes a little more deeper, like why, you know, OFDM is robust against this delay spread. So if you look into these two figures, let's say figure 1 and figure 2, so this multi-carrier modulation actually increases the symbol time by modulating into narrow subchannels. So let's say this is the entire channel frequency response, okay, and you have a dip here, okay, so here you have more fading than here, let's say. So now if you are using OFDM, so basically you are dividing this entire frequency spectrum into smaller subcarriers. So you have this is OFDM for you. This one is the case with OFDM, case 2. So you are dividing into smaller frequencies or smaller subcarriers, and each frequency is seeing only a small part of the channel frequency response, okay. So the effect of, you know, multipath is greatly reduced when you are using OFDM. So the channel frequency responses, so in a multi-carrier system, each subchannel only undergoes a slight distortion, as you can see here, okay. So that is the again, that is the high level concept behind using OFDM and how it is robust to the multipath effects or the delay spread. And the term OFDM, so you have basically OFDM, so this O stands for orthogonal, okay, and then frequency division multiplexing, you already saw that you are basically dividing the entire spectrum into different frequencies, and then you are combining them together, okay. So you are modulating onto different subcarriers, okay, and then you are combining them together here. So this is essentially a frequency division multiplexing, but you have this O, which stands for orthogonal, and the orthogonality is ensured between these different subcarriers. So the spacing of the FB frequencies allows tight packing of the signals, and actually these FBs, they overlap. Okay, and the choice of FB is related to the bit rate to make the signals orthogonal. Okay, so this is important. So if you have multiple signals here, let's say, so this one, let's say these are the different components of OFDM S1, S2, S3, S4, etc., and you are combining them together. So this signal, let's say, is orthogonal to this one, is orthogonal to this one. Or rather, each adjacent signal on two adjacent subcarriers are orthogonal to each other. So the spacing between the signals are maintained such a way that if you do, let's say, let's consider S2 and S3. So S2 is basically, let's say, cosine wave. Okay, so this is 2 pi. I'm writing this one. So this is F0 plus 3b by 2. And let's say S3, the adjacent one, is A cosine F0 plus FB by 2. Okay, so if you try to do this, as you know already, there is a T here, sorry. As you all know from the concept of orthogonality, this has to be 0. So this multiplication integrated over T, this has to be 0, and that will impose some spacing between these two frequencies. So we have done this before. We have done this when we were doing frequency shift keying, and we were trying to have two signals on two different frequencies orthogonal to each other, and we have done this condition before. And actually, you will see, if you do this, the spacing between these two frequencies should be a multiple of 1 over TB, where TB is the bit duration. So the same concept applies in case of OFDM. So you have this frequency spacings, they are chosen in such a way that these signals, if you average over the bit time, or in other words take this integral of two adjacent signals, this will be 0. Okay, and in the receiver you can extract only one of the signals by multiplying the entire composite signal, which is basically a sum of all this. Okay, as you can see from here, so this is, all of them are combined together. So it's the sum of all these small tributaries modulated. So at the receiver, if you just correlate with one of these signals, so this will give you, let's say this is S1, S2, S3 up to let's say Sn. And in the receiver, if you correlate this entire thing with, let's say, S1, if you want to extract S1, then only this component will give you a non-zero value, and because of the orthogonality, all the others will be 0. Okay, and then you can filter out this part. So if there is no corruption in the frequency spacing in the receiver, you are able to extract only the S1 signal. So the difference between OFDM and traditional FDM is that in traditional FDM, the signals avoid the frequency overlap. Okay, so this is the frequency spacings of FDM and OFDM. So you can see, sorry, this is the frequency spacing of OFDM only. This is the OFDM part. So you have this 3 subcarriers for OFDM in time domain, and you can see the spacing FB is basically 1 over T, the symbol period or the bit period, whatever is the modulation they are using. So if it is using a binary modulation, then this T is a bit period, and if it is using MRE modulation, then this is the symbol period. And FB is a multiple of 1 over T, as we were discussing. So this is exactly 1 over T. This spacing is kept as exactly 1 over T, and you have these OFDM subcarriers in frequency domain spaced between FB, twice FB, thrice FB, and so on. And you can see that there is an overlap. Okay, so this overlap is there to tightly pack the signals so that the capacity is enhanced. And if you correlate in the receiver with one of these waveforms, then you will get the signal back whatever you want. So if you want to, let's say, recover this subcarrier, then you correlate with this in the receiver, and you will have a strong component corresponding to this, and the other subcarriers being orthogonal, they will cancel out, and then you can just filter out this part. So this is how OFDM subcarriers look in frequency domain, and this is actually the traditional FDM. And you can see that in traditional FDM they are not overlapping. Okay, so they are spaced a little farther apart. Okay, so that's the difference. Okay, so moving on, so given an OFDM subcarrier bit time of T, FB must be a multiple of 1 by T, as we were discussing. So for example, in IEEE 802.11n wireless LAN, you have this 20 megahertz total bandwidth, and only 15 megahertz can be used for data transmission, and these 15 megahertz can be divided into 48 subcarriers, and the spacing is 0.3125 megahertz. Okay, and then the signal is translated to 2.4 gigahertz or 5 gigahertz band. So again, if you go back to the very first slide, not first but one of the first few slides, so here you can see that this FB, so these are the spacings. Okay, FB by 2, 3FB by 2, and so on. So the adjacent carriers are FB apart. Okay, you can see between these two, this is 3FB by 2 and this is FB by 2, so this is FB apart. And then the central frequency is F0. So this is what is the case for IEEE 802.11n. So the central frequency F0, this is basically 2.5 gigahertz to or 5 gigahertz band. So this entire thing is translated into this band, and the spacing FB is 0.3125. So basically you have this F0, which is, let's say, equal to 2.5 gigahertz or 5 gigahertz, and the bandwidth is 48 megahertz across this. Okay, so this is 48 megahertz. Okay, and then this is divided into 15 megahertz, and this is divided into 48 subcarriers. Okay, so 48 subcarriers. So just an example of a practical system, and then these spacings are 0.3125 megahertz. Okay, so that's what is happening in case of IEEE 802.11n. So this is an example of OFDM. So the benefits of OFDM, as I was discussing, so it mitigates frequency selective fading, because the frequency selective fading only affects some subcarriers, and that can easily be handled with a forward error correction code. More importantly, OFDM also overcomes inter-symbol interference. Okay, So because of the improper time synchronization, and because of the multipath, different copies of the signals arrive at different times, so there could be some inter-symbol interference. Okay, so let's say this is one symbol and then another copy might just be falling on this one, if this is the time axis, let's say. So this is like inter-symbol interference because of another multipath falling over this, because of the delay that, or the random delay that is occurring. Okay, so ISI is caused by multipath signals arriving in later bits, so just like this. And what happens is that OFDM bit times are much longer, okay, by a factor of n. Okay, so you have original signal r bits per second and you are dividing it into n tributaries, okay, of r over n, right, as you saw in one of the first few slides. So because let's say in 1 second, let's imagine that this is my 1 second time interval, so this is 1 second, okay, and you have r bits here, let's say r bits. So so each of these r bits has a time duration of 1 over r, right? Because in 1 second you have r bits, so each of these has 1 over r. And if you're dividing into r by n, then in 1 second you are having r by n bits, okay, so therefore each bit is n over r wide, okay. So compared to this, the bit duration of OFDM is n times larger, so by a factor of n, so this is much longer, and that's why ISI is dramatically reduced, because the bits are spaced further apart like this. So there is a more room, okay, for ISI, okay. So this phenomenon has a less chance to happen because these bits are further apart compared to if they were very close, okay. So this n is chosen so that the root mean square delay spread is significantly smaller than the OFDM bit time, okay. So the delay spread, if you look into a multipath channel, so you will see that there are multiple random delays, okay. So if you recall, let's say your received signal is basically AI times the signal that you are transmitting, and then you have t minus tau I, okay. So this tau I are the delays, and then you have I equal to 1 to m, let's say. So there are multiple delays in the received signal, okay. So basically these are all the same signal, but they are arriving through multiple paths and they are having multiple delays, okay. So therefore you will, if you plot this impulse response of the channel, this will be different taps here with different amplitudes. So these are all your different AI, so A1, A2, so on, and then these delays, these time delays are the different delays, okay. So this tau 1, tau 2, etc., okay. So so if you do a root mean square of this delay spread, so then this n is chosen so that the root mean square delay spread is significantly smaller than the OFDM bit time, and it may not be necessary to deploy equalizers to overcome ISI if you do this, okay. So equalizer is another device that mitigates the effect of this multipath, okay. So by compensating these delays and this fading gains. Okay, so so if you do OFDM, then this equalization may not be required, or it can be less complex. Okay, so this eliminates the use of this complex and expensive devices. So that's the benefit of OFDM. Okay, so let's do an example. So consider a channel with a delay spread of this 20 microsecond, and you want to design an OFDM system for use with such a channel so that the sub-channel bandwidth Bn is equal to Bc by 2. So Bc is the coherence bandwidth, where Bc is the coherence bandwidth of the channel. Now suppose there are 128 carriers in your design. So these are the number of sub-carriers actually. Using the approximation that coherence bandwidth is approximately equal to 1 over Tm, the delay spread, determine the total bandwidth occupied by the OFDM system. Okay, so this is the first part. So let's first look into the first part. Okay, so your Bn is equal to Bc by 2. So that's what is given here, and that's this Bc is 1 over Tm. Okay, so this Bn is the bandwidth of each of the subcarriers. Okay, so there are many subcarriers. So this Bn is basically this, the bandwidth of each subcarrier. Okay, so if you have 128 subcarriers, then the total bandwidth is 128 times Bn. So this is 128 over twice Tm, and everything is given here. So in that way you get 3.2 megahertz as your total bandwidth. Okay, so now let's look into part B. Assuming a constant SNR equal to Es over N0 equal to 20 dB on each subchannel, find the maximum constellation size for MQAM that can be sent over each subchannel with a target symbol error probability of 10 to the power minus 3. And then find the corresponding total data rate and bandwidth efficiency of the system. Okay, so first thing first. So MQAM, and it's nothing is mentioned here. So let's assume that it's a rectangular constellation. So for a rectangular constellation, we have studied this before. The probability of error is approximately given as this. Okay, and therefore here your Es by N0 is given, which is 20 dB. So that will be 100 in terms of ratio. Probability of error is 10 minus 3. So if you just replace everything here, only M is unknown here, and if you do the math here, then M comes to be roughly 26. So your M appears in the denominator here, so you have to have at least a probability of error of 10 minus 3. So so this argument of the Q function has to be more. Okay, whatever value of M you get here, 26, if you put 26 here, and then you will get 10 minus 3, but you have to get a probability of error greater than 10 minus 3. Okay, so at least 10 minus 3 should be ensured. So so the nearest power of 2, which is less than this 26, is 16. Okay, so assuming M to be a power of 2, we would have M as 16, because if we choose M more than this 26, then this ratio will be lower. And if it is lower, if you see the plot of Q function, Qx over x, so if it is lower, then the probability increases. Okay, if you go this side, then the probability decreases. So we have to ensure, if this is the point corresponding to your 10 minus 3, and that gives your M to be 26, you have to choose an M which is less than this, so that the denominator is small and this term goes up towards this direction, so that you have at least 10 minus 3 or lower. Okay, so that's why we are choosing m to be 16, and this is also a power of 2. So now with that, the data rate will be given by this Nyquist formula, and B is your bandwidth that you calculated. Okay, so you will have 25.6 megabits per second, and the total bandwidth is 32 megahertz. So the bandwidth efficiency is how many bits per second you can transmit per hertz of bandwidth, and that is 0.8 bits per second per hertz. So that's the concept here. Okay, so now let's move on and let's see how OFDM system could be implemented. Okay, so let's consider an MRE QAM system. So it uses frequency band centered on the frequency fc plus fi. Okay, and you have these symbols denoted by AK and BK. So basically these AK and BK, these are the different points on the MRE constellations, MRE QAM. So let's consider a constellation like this. So if you have an MRE constellation like this, so these are basically the coordinates of the signal AK and BK. Okay, so this means if you consider this as, let's say this is 16 QM, let's say in the figure that I have drawn here, and if you choose the distances, like let's say this is d by 2, this is minus d by 2, okay, and this is minus d by 2, this is also d by 2, and then these are different multiples of d by 2. So this is like let's say each of the signals are d apart, so this will be 3d by 2, and this will be minus 3d by 2, this will be again 3d by 2, and this will be minus 3d by 2. So with that geometry, each of these AK and BKs will be either plus minus d by 2 or plus minus 3d by 2, etc. So for 16, this will be only plus minus d by 2, plus minus 3d by 2. For general AM, this will be square root of m minus 1 d by 2 plus minus of that, where m is a square number. So for square constellation, this AK and BK will have this form. Okay, so these are the coordinates of the symbol. Okay, and you are basically, if you choose the orthogonal axis, let's say phi 1 and phi 2, so if you choose your phi 1 as cosine and phi 2 as sine, so these are basically your orthogonal basis functions. So you are modulating basically with these carrier frequencies which are centered around fc plus fi, and then you are adding them to get st. Okay, so let's consider this MRE system. This is basically, this is not yet OFDM. We will gradually develop the concept of OFDM. So this is a general single carrier system. This is not a multi-carrier system. Okay, so remember, OFDM is a multi-carrier system. Okay, but this is a single carrier, so we have a single carrier FC. Okay, so we are using the in phase and the quadrature of that, and then we are generating a signal ST, and then this signal ST can be received in the receiver, where we are correlating with the carrier frequencies or the basis functions, whichever way you want to call it, and then if you integrate it over the symbol duration, then you get the estimates of AK and BK. Okay, so now we adopt an equivalent model for this QAM system, which is shown in the figure below. So this is the equivalent model. This will make our subsequent analysis easier, and the proof of this equivalence of the two models is left as an exercise for you. Okay, so here you have CK, which is AK plus JBK. So you have a complex representation now. So if you go back to this representation, so phi 1, phi 2, and let's say this is the general position of a signal in a constellation. Let's say there are the other signals here. Okay, let's say I'm considering only one signal here. So if this is AK and BK, so basically the distance from the origin gives you the energy, okay, and basically the distance from the origin gives the amplitude of this signal, and the angle it makes with the phi 1 axis, the positive direction of the phi 1 axis, is the phase. Now if you just imagine that this is the real plane and this is, the real axis, and this is the imaginary axis, then you can represent this same as a complex number, where you can say that this signal is equal to CK, where CK is equal to AK plus JBK, and both representations are equivalent. Okay, so if you have CK, which is AK plus JBK, and then you are basically modulating it with this frequency to get FT. Okay, so you can see that the FC part is removed, because the FC part is common, and it's the carrier frequency, so only the Fi part is there. So if this is again this is a phase amplitude representation. So when you have a phase amplitude representation like this, then basically FC is the frequency with which this is, let's say, rotating. Okay, so, and the particular angle that it is making is the phase. Okay, so FC plus that angle is the total angle of the signal. So this is not part of this module, so I'm not discussing this in detail, but the point is that this is equivalent to the representation in the previous slide. So you have FT, which is the complex representation of the symbol multiplied with this phasor. Okay, and then this is the transmitter and this is the receiver. Okay, so now with that let's move further. So the signal FT that you saw in the previous slide, FT, this is again a complex signal which is not suitable for transmission directly, but is processed as follows. So if you write FT equal to UT plus J of VT, so real and complex part, and then if you use UT to modulate the carrier and you use VT to modulate the quadrature carrier, then you have a representation like this. So basically this is a different representation. This is the in phase and the quadrature representation. So ST in the diagram here is basically the FT. Okay, the FT times exponential of this term, which is the carrier frequency, and real part of that. Okay, so basically this is your, these two together form your FT. Okay, which is basically UT plus JVT, and the real part is modulated with the in phase component of the carrier, and the complex part is modulated with the quadrature component, and then if they are combined together, then you get ST. Okay, and that ST is sent through the channel, and this is the real part of this. Okay, so this is basically a regular time domain signal. okay, which you can represent physically. So that is transmitted through the channel, and then in the receiver you do the opposite function. You correlate with the carriers, and then if you do this multiplication in the receiver, this will give you the signal term, or the difference frequency and the sum frequency. If you're multiplying two cosines and two sines, you will get the sum frequency component and difference frequency component. You want the difference frequency component to retrieve this ut and vt, so you are passing this through a low pass filter to retrieve ut and vt. Okay, so that's what is ft here. So ft basically is represented by ut plus jvt, and then the actual signal st is this. Okay, so then and then the ft, which is ut plus jvt. So ft is ut plus jvt, and you are actually sending st as the real part of ft times e to the power minus j 2 pi fct, right? So this ft now can be represented as this. So ft is basically now if you want to incorporate n subcarriers, you can say that you have different complex symbols which are denoted by capital F0 bar, capital F1 bar, up to capital Fn minus 1 bar. So these are different complex symbols that are picked up from a constellation, okay, like this. Okay, so each of these F0 bar, F1 bar are one of these. Okay, and each of them are modulated by a subcarrier, and these subcarriers are delta f apart. So this is, let's say, 0. This is twice pi delta f, so up to twice pi n minus 1 delta f. So there are n subcarriers, and then you are adding them all together to generate ft. So you can write ft as this. So this is the sum of 0 to n minus 1 modulated signals. So each of them are picked from a constellation like this. Okay, so and you can see that they are spaced delta f apart, and delta f, according to OFDM requirement, to be orthogonal has to be 1 over TB or 1 over TS, whatever. Okay, so this FT is then again received, and you do this do the correlation operation in the receiver to get back these symbols, capital F0 bar to capital Fn minus 1 bar. Okay, so the symbols Fm, as I was saying, these are complex symbols that are picked from a QAM constellation like this. Okay, so for 16 QAM we will have this AM and BM will be from these quantities. Okay, and the different FM may use different sized QAM constellations, so we shall see later on why this can be a good idea in practice. Okay, so let's say this m small m varies between 0 to n minus 1. Okay, so for m equal to 0, so f0 can be from this QM, okay, which is a 16 QM. Okay, the f1 can be from another QM, okay, not necessarily this one. So all these individual subcarriers can come from a different QM constellation. Okay, so basically each subcarrier can come from a different constellation, and then on top of that they are modulated with these with this with these carrier frequencies. Okay, so so moving on. Okay, if you have ft like this, and st is therefore, as we were saying, is the real part of, so st was the real part of ft times exponential j, right? So so if you do this, then we will have st is basically this equation. So this is the real part, so you replace ft here, okay, and this one, so we'll have fc plus m delta f, so fc plus m delta f, and j 2 pi of that times t, and these fm's come from ft, and then the real part of this. Okay, and then fm is basically this capital Fm is am plus j bm. So basically we have this simplification. So this is the time domain OFDM signal. Okay, so here you have all the information here. Here you have all the n subcarriers from 0 to n minus 1, and the central frequency is fc, and then they are delta f apart. Okay, and you have the in-phase component and the quadrature component. Okay, so so these are spaced at a frequency separation of delta f and occupying a frequency band lying approximately between fc and fc plus n delta f. Okay, so usually fc is very greater than delta f. So as you could see from the example before, we discussed the Wi-Fi WLAN example where fc was like 2.5 gigahertz or 5 gigahertz, and delta f was like 0.3125 megahertz. So basically fc is very greater than delta f. Okay, so now so this is the implementation of OFDM. Okay, so now this capital N, like what if this is like more than 1000? If you have 1000 subcarriers, okay, are you going to have 1000 branches like this? Okay, this is not very practical. So if you have 1000 subcarriers, you need 1000 oscillators. Okay, so each of the subcarriers would be modulated by a different frequency, which is delta f apart. So if you have 1000 subcarriers, then you have to multiply in your transmitter the complex symbols with 1000 different frequencies, and then in the receiver also you need to have 1000 oscillators to do the correlation operation. And this is not very practical because this would require lot of hardware complexity and very high power consumption. So then what do we do? Okay, and let's see what can we do. So in general, the expression for OFDM, I mean the ft is this. Okay, so if you substitute delta f equal to 1 by t, because delta f is a multiple of 1, or actually exactly equal to 1 over t for the subcarrier separation, then you have this expression. So now let us sample the time domain signal ft. So if you sample the time domain signal ft, which is given by this, then you will basically get these samples. Okay, which is this signal sampled at regular intervals. So this is identical, this expression of fn, which is the time domain sample, each sample is identical. So this f small n is one sample. Okay, so each sample is identical expression to the endpoint IDFT of the complex modulated symbols FM bar. So here comes some concepts of your digital signal processing. So this is an endpoint IDFT, capital N point IDFTs, where capital N is the number of subcarriers. Okay, so instead of having n oscillators, if your n equal to 1000, you are having 1000 oscillators. You can have an endpoint IDFT. Okay, so you eliminate the need of all those oscillators. So let's say your signal, which is, let's say, RB bits per second, you do a serial to parallel conversion to do like generate n tributaries each of bit rates RB by n, and each of them is modulated or mapped basically onto a symbol from a different QAM constellation. So let's say for capital F0 bar, we take it from M0 QAM modulator. For F1 bar, M1 QAM. So all this QAM can be different. This can be QPSK, this can be something else, and so on. So, but each time you are picking it from a fixed modulator. So for F0, you are having the same constellation always. So these are all the bits coming serially. So let's say 0, 1, 0, 0, 1, 1, 0, 1, and so on. Okay, so you are dividing it into different tributaries, and then let's say if your n is if your capital N is, let's say, 64, okay, then let's say whatever number of bits, like you can take let's say this M0 QM is a 16 QM. Okay, let's assume for the time being that each of these is a 16 QM. This can be different. So let's say if it is a 16 QM, then at least you have to pick 4 symbols together, because in a 16 QM each of the symbol represents 4 bits. So at least you have to have 4 bits. Okay, so you have to divide the original stream into 64 tributaries, and each of those 64 tributaries should have at least 4 bits. Okay, so if it is a 16 QM, and then those 4 bits based on the pattern here. Okay, so let's say we are dividing the tributary into 4 bits. Okay, so this is divided into 4 bits. Okay, so you have to have 64, at least 64 such copies. So 64 times 4. So from the input stream you have to pick 256 bits at a time. Okay, let's say you are picking 256 bits at a time, divide it into 64 tributaries, and then each of them are, let's say, a 4-bit symbol. Okay, so the first one is mapped onto this QM, and whatever is, let's say, 0100 equivalent to that. Sorry. So that is basically the corresponding F0 bar. Okay, so let's say if you have a 16 QM, so let's say this 0100 corresponds to this. Okay, so this particular, whatever AK and BK this has, that will be or rather AM, sorry, for F, capital F we were using this notation. So this is your FM, which is basically AM plus J of PM. Okay, so that is let's say F0. For F1 you also have a separate QM from where you are picking up a symbol. And these QAMs, here we are taking an example that all of them are 16 QAM, but that may not be the necessary case. This M1 could be 64 QAMs. In that case, your second symbol has to be 8 bits long. Okay, because sorry, 64 is 2 to the power 6, so it has to be 6 bits long. Okay, so and then you map that to that constellation and choose F1 bar and so on. And then once you obtain this F0 bar, F1 bar up to Fn-1 bar, then you do a capital N point IDFT, okay, to obtain this time domain samples, small f0, small f1 up to small fn-1. And then the next block is adding cyclic prefix and do parallel to serial conversion. So the cyclic prefix part we will discuss later. Let's ignore this part. And then you have some pulse shaping, and then you have the in-phase part and the quadrature part, which is modulated into two carriers, okay, and then that is combined together to get the final OFDM symbol, okay. And this part actually generates this, which is equivalent to this, okay. So this is basically the IDFT part. So we are doing endpoint IDFT to eliminate the usage of all those N oscillators, which is not practical anyway. Okay, so this is how the OFDM transmitter works. In the receiver we just do the opposite. So we first demodulate, okay, and then remove the cyclic prefix and do serial to parallel conversion to get the output samples. And in the transmitter we did IDFT, so in the receiver we have to do FFT to get these complex symbols. And then you have the exact similar demodulators, M0 QM, M1 QM, and so on. And after the demodulation, you have the parallel to serial converter to get back the original bits of the OFDM symbol, okay. So now so this is this we have already discussed. So this is the summary of how OFDM is implemented. Let's look into the cyclic prefix part, which was ignored. So so OFDM's long bit times eliminate most of the ISI because the bit times are n times, so they eliminate most of the ISI. But on top of that, we use a cyclic prefix to overcome the residual ISI, okay. So what happens is that this cyclic prefix, basically this adds additional time to the OFDM symbol before the real data is sent, okay, and they are called the guard intervals, okay. And ISI diminishes before the data starts, okay. So how is this cyclic prefix generated? So basically, if you have your data from x1 to xl, so these are the different symbols, okay. So the last V symbols are copied first, okay. So basically whatever you have, so serial to parallel and then IFFT, and then you have the last V added in the first, and then you do the parallel to serial conversion, okay. So this is called cyclic prefix. Uh, so the advantage of doing that is this. So let's imagine then that you have different blocks of the OFDM symbols. So this is the L minus 1th block, this is the Lth block, this is the L plus 1th block. Okay, so now so this is the direct wave which has different blocks of OFDM, and these are the two reflected waves which are a little bit time lagged. Okay, so you can see there is a time lag here, there is a time lag here. So these are the delays. Okay, these are the reflected waves and these are the delays. Okay, now when you are receiving the signal L, this block, okay, so this, imagine that this is the receiver window. Okay, so you are just observing these symbols that are present in this block, which is denoted as L. So in this window you will have some portion, because of these reflected waves and the delay, you will have some portion of the reflected signal. So this is basically these are the part of the previous symbol. So L is my block of interest, but I receive some part of this one, and here also some part of the previous one. So this is the part from the previous symbol, and these are interference from the previous symbol. We don't want these parts. Okay, so now if you add cyclic prefix, where a copy of the last few symbols are added first, then because of this delay and because of the cyclic prefix, let's say this is the receiving window now. So here even if these are the reflected waves, so we don't have the part of the data of the previous blocks in the receiving window. We have the part of the cyclic prefix. Okay, so these are the cyclic prefix part, not the data part. Okay, so ideally the maximum delay that you can have is basically the length of the cyclic prefix. Okay, if this delay the maximum delay, if it is a further shifted part, so maximum you can have a delay like this. Let's say the entire cyclic prefix falls here. Okay, so that at most you can handle. So the delay that you can mostly handle is a situation where the entire cyclic prefix falls within the receiving part of the Lth block. Okay, anything more than that, any delay more than that, if you have further more delay, then we have, let's say this is the cyclic prefix, this is the data, and then we have the data from the previous block. Okay, so this part is the data from the previous block. So at most you can have a delay that is equal to the cyclic prefix length. Okay, so the choice of cyclic prefix actually depend on the maximum delay spread of the channel. So the maximum delay spread whatever is the length of this and the total cyclic prefix length can be equal to this. Okay, so in that way you can eliminate the effects of ISI. Okay, so I'll stop here for this particular lecture, and then I will complete the remaining of the OFDM concepts in the next video lecture. Okay, thank you.